Okay, welcome to the pre-class video assignment for section 1.4. In this section, we're going to look at our first method for solving differential equations. The method here is something we call separable equations. So we can use this method to solve certain DEs if they fit a certain description here, and that is what we call being separable. So as the little definition up here describes, a first order a DE, dy dx equals f of xy. So this is our generic first order DE. This method doesn't work for any old DE. It works specifically for the type of DE where the f of xy we're looking at is equal to g of xy, g of x times h of y. So if this guy here is up in here, if this is the type we have here, then we have a method here that we can use to solve. So a little bit about separable here, some examples. A couple of, so 4 examples here. Determine whether the following DEs are separable or not. So here's a first one here. Again, we're really looking at this function here. This is the f of xy function. Can it be written as g of x times h of y? So a function of x times a function of y. So this one can be, with just a little bit of work, using rules of exponents, we can actually rewrite e to the x plus y as e to the x times e to the y. And then we can rearrange the factors. So we can write 2x e to the x times y e to the y. And indeed, this is separable. So the first one is a yes. This first one is separable. The second one, again, to see if it's separable, the first goal would be to move everything over to the right-hand side. So dy dx here is equal to x plus y divided by x. Now that is not a product of functions, a function of x and a function of y. You can try and play around with it a little bit. So this is equal to x over x plus y over x. This is therefore equal to 1 over y over x. However, this is still not separable. I cannot express it as just a product of a function of x times a function of y. So this could be, this y over x is 1 over x times y, but then we still have this 1 plus over here. That has to be involved in one of the products, and that cannot be written as separable. So this one is not separable. The next one is 2 dx dt equals x. So in this one here, again, we want to think about everything on the other side. So divide both sides by 2 and we get dx dt equals x over 2. Note the name of the variables has changed. We now have x as our dependent variable. The x is now the name of the function, and the independent variable is called t. So now we're really looking to see, can we write this as a function of t times a function of x? And this is actually true in a trivial sense. Yes, there is no t over here, so we can think of this as being a constant function of t times a function of x. So we can see it or envision it in terms of this definition of separable. So this one is indeed separable, if in a somewhat trivial way. This one is indeed separable. The last one is actually an example of something we will talk about later in the course. So this DE rather looks messy. You might look a little odd because we have the dx and the dy separately, but you can use algebra to rearrange it and make it look like dy dx equals. So when we write a DE in this form, this is called the differential form of a DE, and this is a topic we will see later in the course. But realize for now that we would just want to rewrite it so that it says dy dx equals, and then we're trying to judge whether the stuff on the right-hand side is separable or not. And this one looks a bit messy, but it's actually quite easily separable, yes. So this one is indeed separable. So that is our first skill, recognizing whether a DE is separable or not. All right, so then what is the method? Given that we have a separable DE, how do we go about solving the DE? That is, how do we find the function that solves this differential equation? So here are a couple of little things here. There's a trivial case here. First of all, if the h of y function is just a constant function 1, then notice the dE just becomes dy dx equals g of x. This is nothing special. That is just a calc 1. It says dy dx equals a function of x, and I want to know what y is. So this just says just integrate. If you integrate g of x, you would get the function y. So again, this is just calc 1. Yes, you can integrate on both sides, and we would get y equals big G of x plus c. Of course, a constant is generated. This is our solution family because this constant is generated. So that is kind of a simple case, not really all that important in terms of the method. So the less trivial case, what happens when h of y is not equal to 1? So if the h of y is not equal to 1, the idea is that we can separate the g of x and the h of y. We can collect the y's on one side and the x's on the other side, and we end up with something that looks like this. 1 over h of y dy equals g of x dx. Now, if you take a quick look at that, this looks rather suggestive. It looks like, well, this looks kind of like integrals on both sides. So the question is, can we just integrate this on both sides to get a solution? The answer turns out to be yes. However, it is not as obvious as it first looks. So yes, if you have an equality, you can integrate it on both sides. But the difference here is that this is integral on both sides, but on the left-hand side, the integral is dy, and on the right-hand side, the integral is dx. So we're not actually even integrating with respect to the same variable. So it is not actually all that obvious that this works. It turns out that it does work, but it is not immediately obvious. So that is sort of our issue. It is intact process, integrating both sides, but is this valid? So just a quick little idea here to see why this might actually be okay. So a justification of the method of just integrating on both sides. So just briefly, this is sort of a light proof of the method, if you will. But again, if we start with the dE that we have converted into this form, and let's assume that y equals phi of x is a solution to this dE. So we're running out of convenient letters to use for functions. So here we're using y equals phi of x, the Greek letter phi. But again, let's assume that this is a solution to the dE. Note then, if y equals phi of x, you can differentiate on both sides and get that dy is phi prime dx. Then, since y equals phi of x is assumed to be a solution, if we plug it into this dE, it would have to give a true equation. So this is what we get here. This would have to be true because I'm just plugging in a solution function into the dE. Notice what we have here then. At this point, if I plug this information in, so again, I replaced y by phi of x, I replaced dy by phi prime of x dx. If I look at this guy now, this equation, which we know to be true, is now both with respect to d of x on both sides. And so now you can simply integrate on both sides with respect to x. And that is a valid thing to do. Notice, to sort of see it a little bit further still, effectively on the left-hand side, all you really have is a u sub. If you let u be equal to phi of x, you get 1 over h of u, and then du would be phi prime of x dx. So you get 1 over h of u du. So this is what we get, and this is our method, right? This is basically what we wanted to do in the first place. We wanted to integrate on one side with respect to one variable, integrate on the other side with respect to x. Again, now because I used a u sub, this ended up being in terms of u on the left-hand side. The name of the letter is not important. I could have done a y sub here and ended up with 1 over h of y dy, and that would have been what we were hoping to use for our method. So again, that is really just a little justification that this works. All right, so a couple of examples. The first one here is actually a trivial one. So this one is just a trivial example because this one is one where simply we have dy dx is a function of x. So to solve this for y is to just integrate. Notice that if you don't really notice that and continue normally and separate as the method suggests, it's fine. You still get the same answer. So by separating, I would consider this as being a 1 dy on the left and an x minus 1 squared dx on the right. So we integrate on both sides. Integrating on both sides, we would want to basically expand this polynomial out, and then we can integrate term by term. So integrating on the left, we would get a y plus c1, and integrating on the right, we can integrate a polynomial rather easily. And again, we generate a second constant c2. So one thing to note here is that, yes, in theory, I generate a constant of integration C1 on the left and a different constant of integration C2 on the right. But since they are both unknown constants, you can always just go ahead and combine them into a single constant. So again, I'm not going to keep writing C1 on one side, C2 on the other side. We will just pretend we always know that we can combine them into a single constant. And for convenience, we will write it on the right-hand side. So this would be our solution. And notice this is exactly what you get if you just integrate x minus 1 all squared. So nothing, that one is a rather trivial example. So here is one that is a bit more interesting, a bit more of our method here. Here is our dE, dy dx equals x over y squared. Notice this is separable. This is x times 1 over y squared. So separating, we get y squared dy on the left and x dx on the right. And again, we can, as we justified, we can simply integrate on both sides. So again, these integrals are pretty easy. If you integrate on the right, we get a 1/3 y cubed. If we integrate on the if we integrate on the left, we get a 1/3 y cubed. On the right, we get a 1/2 x squared. And again, we take both constants of integration and roll them into a single constant on the right-hand side. That is technically a solution to our dE. However, it's not very nice. We call this an implicit solution because it is not solved for y. It does not say y equals and then a function of x. So we always prefer an explicit solution if we can do that. So that is solve for y if you can. So solving for y, see what happens. We can multiply both sides by 3. We can then take the cube root on both sides, and we would get something like this. Notice what happens with the constant. If I multiply both sides by 3, I have a 3c over here. Now, if c is an unknown constant, 3c is an unknown constant. So we generally wouldn't just call it 3c. We would just call it like a constant. So you might call it C1 or give it a different name. It's sort of bad form to just call, if this is C, then this shouldn't also be C because it's not the same constant. But if this was C1, this could be C2. But in the end, we don't really need an index there. So I just went ahead and called it K for my constant in the end. Another extremely important thing that makes math teachers happy at this point, and that is we finally reached the place in calculus where the plus c is no longer this throwaway redundant thing that you have to remember to stick on the end. Notice that it is important to recognize the constant and then keep recognizing it as you solve, because now the constant is not just a constant added on the end. It is now involved in our formula, and it is important that we recognize where it comes up in our formula. Again, this is a family of solutions. Every different constant value for k represents a particular solution from this family, but it is not just a constant added on the end. So that is important to notice. So give this a go. So here's a little example to try it on. And as you may have noticed in that last example, some of the questions might also involve an initial value problem to solve. So you may need to also sort out what the constant is in order to solve the initial value problem. That's somewhat common in some of the questions on the website because that makes for easier coding of questions if we don't have to deal with this unknown constant. But again, you should be able to solve the initial condition that as an extra step fairly easy. So try another one. All right, so that's basically the first 2 pages of the notes for 1.4. We will finish off talking about these notes in class together. Before we go, we also want to talk about some prerequisites for this section. So there are some things we need to I would like you to look at to review in terms of integrals that we will run into in this section. So that we will run into a few integrals in this section. Some of them might be tricky. You might need to remind yourselves a little bit. So that's kind of what these next few exercises are for. So you will have learned in Calc 1 the idea of U substitutions. So again, we sometimes run into U substitution situations involving trig functions. So that's your first example. Once you have that example, another thing we learned about probably in Calc 2, in fact, I should say the remaining techniques were probably something you would have learned in Calc 2. One is we need to be able to do the integrals of rational functions. So for integrating rational functions, in theory, the first thing we look at is whether we need to long divide in order to integrate. So if a rational function has a numerator that is the same or higher degree than the denominator, then you should long divide before integrating. So give that a go here. All right, once you have long divided, or if your question did not need to be long divided first, the next general approach to integrating rational functions is to perform a partial fraction decomposition, a PFD for short. So this particular example you're about to try is a fairly straightforward case 1, type 1 partial fraction decomposition, but you might want to dig out a calculus book if you don't remember partial fraction decomposition and remind yourself how that works. But here's a little one to practice on. Lastly, I have thrown in some, I'm calling these some basic integrals resulting in natural log functions. So these are actually also things that can be done as a U sub. You can also kind of remember them as a rule from calculus. So this tends to be, how do you integrate 1 over ax plus b? You can do them by little U sub. So practice that for this next examples. And then last but not least, integration by parts. So we will see a fair bit of integration by parts. I think you'll see this next one and the final one for this section is a bit tricky, but the question is scaffolded, and that is it's going to lead you through the method for integrating ultimately by parts in this next example. So give that a go. Okay, so basically, we will finish up the section 1.4 together in class. We will be running into integrals of these types through the section. So it's just a good idea that you have seen some of this beforehand, and we can not get bogged down in those integrals while we're learning this new method. Anyway, that's it for this section. Thank you very much. We will see you in class.